And yep, our today topics, if you see here, the today topics, if you still remember from our last week class, we also have the topic relative motion. But from last week, is the relative motion based on the translating axis. Translating axis means if we have the global frame and we have another reference frame, just translate from the original of the global frame, but the orientation of the axis, the orientation of the axis still be the same with the global frame and doesn't change the orientation. But for today's class, rotating axis means we consider the frame that is not only change the origin from the origin, but it also change the orientation. And in some problem, the rotating axis is useful for the analysis of the problem. So today we will see how can we apply the idea of the rotating axis. And we begin the new topics. First, we explain the theoretical support about the rotating axis. We explain the derivation of the velocity and the acceleration and show you the example about the rotating axis. And at the end of the class, we will switch back to one example from our last week problem. We have one example that we still didn't complete. And yeah, today the main topic is the relative motion with the rotating axis. We will see the concept of this idea, and we will derive the velocity and the acceleration. And one complicated term, one component of the total acceleration for the relative motion is Coriolis acceleration. Many times, maybe in physics class or maybe in our before midterm class, we mentioned about this before. And today, I think by the graphical explanation, we can get a better understanding about the Coriolis acceleration. And of course, for rotating axis, we have many examples to show you what is the useful of this technique. But for today, I prepare only one example, and we still faster than the schedule. It means next week, we're gonna review many examples related to the relative motion in the rotating axis. And in next week, I hope most of us can attend the class, because last 30 minutes of the class next week, maybe from 3 p.m., 3:30 p.m., Ajahn Lim will assign the term project for our class from next week, next Friday, oh no, next Wednesday. So next week, I will begin the class and give you more example for the rotating axis. And at the end of the class, Ajahn Lim will join us to assign a project. Okay, the rotating axis. As I mentioned, we have the global frame. And we have another frame that attached to rigid body. In the previous class, for the translating axis, the moving frame has the same orientation with the global frame. But in this class, the moving frame can change the orientation, from the original orientation. It have the theta that make with the global frame, and it also can be described by the angular velocity and angular acceleration of the frame. And let's see this equation. The position vector of point A with respect to the global frame, the position of point A can be described by the origin of the coordinate frame at point B, the origin of the XY plane at point B, and have the vector combination. So the position vector of point A in the global frame can be described by the position of point B. And in this case, at point B is the origin of the coordinate XY, and have the relative position vector. What is the relative position vector? If we consider point A, with respect to the point B in the coordinate XY, we can see that the point A can be described by X and Y position of the coordinate X and Y. So this distance is X in I direction, and this distance is Y in J direction. I is the unit vector in X direction, and J is the unit vector in Y direction. But we need to remember that for the rotating axis, the X can change the direction. Y also can change the direction. It means that if we consider the time derivative, of the unit vector I, it's not zero. I think we still can remember this idea when we want to obtain the time derivative of the unit vector. Before this, we try to obtain the time derivative of the nt coordinate, if you still remember. But today, we use the similar idea to obtain the time derivative of the unit vector I and j. Please check this diagram. Do you have any idea for the di by dt? Di by dt. We have the x and y direction, and before rotation, the unit vector I and the unit vector j point to the x and y direction. After the time passed with a short duration of time, the direction shift from the original direction x and y to x prime and y prime with the small angle theta. So you can see that d theta here this vector is the change of the unit vector I. We have I and we have I prime. We have I and I prime. So this small distance here is di, the change of the unit vector. We know that the magnitude of the unit vector is equal to 1. The magnitude of the unit vector is equal to 1. And with the small angle here, d theta, when the radius multiplied by the angle, it can estimate the distance here, the length of the vector here. So di can be estimated from the magnitude of the radius multiplied by d theta. And what is the direction? What is the direction of this vector? The direction of di is point to the same direction with y direction. It means j direction. So di is d theta with the unit vector j, and di by dt is d theta by dt in the direction of unit vector j. By using the similar concept, j dot, the first time derivative of the unit vector j. The unit vector j, the original one, is this vector. When the time pass, the unit vector j rotate, and the radius or the magnitude of the unit vector is equal to 1. The angle is d theta, and the direction of the vector, the direction of the vector is in the negative I direction, negative I direction. So the first time derivative of unit vector j by dt is minus d theta by dt in I direction. Just a review. So why we need this? Why we need this? Because we come back to here. We come back to here. The position of the point A in the global frame X and Y, the position of point A in the global frame X and Y can be described by the position of the origin of the frame, the moving frame, and plus the relative position in XY coordinate. And the relative position in the XY coordinate can be described by X component in the unit vector I and Y component in the unit vector J. And I and J is the direction of this coordinate. For the position, it's not difficult to understand, right? For the position, the origin of the frame and the relative position. What is the first time derivative? What is the first time derivative of this equation? RA dot is equal to RB dot plus d by dt of xi plus yj. RB, RA dot and RB dot. We don't need to consider the change of direction of the unit vector because the position of the RA and RB are respect to the global frame, and the unit vector of the global frame doesn't change the orientation. So RA dot and RB dot is just a translation of the point. And to consider the first time derivative of the relative position, to consider the first time derivative of the relative position, we need to have x dot in I direction, and we consider x as a constant and consider the change in direction of the unit vector I. And we consider y dot in j direction, and we consider y as a constant and consider the change of the j unit vector. And it's gonna be this expression. We can separate the group of this and this when we still consider the direction of I and j. And this one, consider the change in direction of I dot and j dot. I want you to check this again. We can see that finally they try to write the thing in terms of the omega. What I want to tell you is, can we write this by I want you to recheck this. If this one is true, d theta by dt, the magnitude is omega. And I want you to consider the omega. Omega is the magnitude of the angular velocity. If we write the omega as a vector, what should be the direction of the vector omega? Omega will point in the k direction, right? Because on the screen we have I direction, we have j direction, and omega is perpendicular to the plane of I and j. So by the right hand rule, is you use the right hand, and if you use your thumb to point out from the screen at point B, and use your finger to follow the direction of the omega, you can find that if you want to compose the vector of omega, omega will point in the positive k direction. And what happens if we use the omega crossed by I? Omega crossed by I. We have the unit vector ijk. We have the circle of the unit vector ijk. I cross j will have positive k. K cross I will be positive j. So of course, for here, the omega in k direction cross I is equal to the theta dot in the j direction. How about this one? I want you to check this. I'm gonna say that j dot is equal to the vector omega k and crossed by j. Do you think this one is true? We have I, j, and k. We have I, j, and k. K cross j will be minus I. K cross j will be minus I. So this one is also true. Omega crossed by j will be minus theta dot I, which is equal to j dot. What I want to say here is, again, if you want to find the time derivative of any vector on a rigid body with the angular velocity omega, you can cross that vector by the omega. if you want to find I dot, and I direction is a vector that moving with a rigid body. If you want to find I dot, you just use the omega vector and cross with that unit vector that you want, and then you got the first time derivative I dot. If you want to find J dot, and J is moving with the rigid body and have the angular velocity omega. If you want to find J dot, you just cross the vector J by omega, and you're gonna have J dot. And actually any vector, not only I and J, if you have vector, for example, this one, the vector R, and the vector R is moving with the rigid body and have omega. If you want to find R dot, you can simply obtain R dot by omega crossed by vector R. But this should be true only when we are not consider the change in the magnitude. If we not consider the change in magnitude, but if we need to consider the change in magnitude, we need to have one more term that consider the change in the magnitude of the R. Again, this one only true when the change in the magnitude is equal to 0. So it's not universal. So ignore this one. Come back to here. R dot A, RA dot equal to RB dot, and plus the time derivative of xi plus yj. The first time derivative of xi plus yj, we have x dot in the direction I and x with the I dot. We have y dot in direction j and maintain magnitude y with j dot. And of course, for these two terms, it's nothing difficult here. But the x I dot plus y j dot, x I dot plus y j dot, omega k cross omega k cross xi plus yj. I want you to see this one I dot is equal to omega k cross I. If you multiply I dot is equal to omega vector cross I. X I dot you just multiply x you may say you're gonna multiply x here or multiply x here, but x is just a constant. You may multiply x to the first term or the second term, but it's true that if I dot is omega cross I, xi dot is omega crossed by xi, and also for the j dot, j dot is omega crossed by j. What about y j dot? Y j dot can also be write as omega crossed by y j. And for here, this just show how we represent these terms by the omega crossed by the relative position vector, omega crossed by the relative position vector. And this term, the last term, this one, we name this term as relative velocity. Relative velocity is measured with respect to the moving frame in the I and J direction of the moving frame. And if an object has the change in the relative position in that coordinate, we can obtain the relative velocity in I and J direction of the coordinate. We come back to recheck this picture again. We have some meaning in this picture. Now, if you see the picture, we can see only the point B and point A, right? We can see the point B and point A. The rigid body, as shown in the shade area, is described by the coordinate x and y. On the rigid body has one point P, and point P is fixed to the shade area, is fixed to the rigid body, fixed to the frame x and y. It means that the relative position of P with respect to B will constant, but point A can run along the slot, and point A can have the relative position with point P. So this is nothing complicated. They just show that the position vector of point A, the position vector of point A can be described by the velocity of point A can be described by the velocity of point B or the origin of the frame. And the velocity of P with respect to B, because the frame is rotating, but point P is fixed on the frame. It means the vector R here, doesn't change because the point P is fixed on the frame. And the velocity of P with respect to the origin B can be computed from omega crossed by the position vector. And of course, the relative velocity of P with respect to B will perpendicular to the position vector and have the magnitude equal to the omega multiplied by the radius. But you should be reminded that this is the velocity of point P, and point P is fixed with the moving frame. But if we consider point A can be another point that just coincident with point P at one time, but point A itself can be moved along the path and can have the relative velocity and relative position against the moving frame. So yes, these two equations are the same. The velocity of point A is equal to the velocity of the origin of frame B. And the relative position, the relative velocity of P is a fixed point, can be obtained by omega crossed by R. But we need to consider that point A can move from the point P. Point A can move from the point P with the relative velocity. And yeah, we have this equation. Until now, we derive the relationship of the velocity. The next step will be a little more complicated, but we are going to talk about the acceleration. So please remember, maybe let me think. Okay, we're gonna keep this equation to the next page. VA is VB plus omega cross R and the relative velocity. VA is equal to the VB of the origin plus omega cross R, which is the omega cross R will be the velocity of point P that fixed to the frame. And we have the relative velocity for the step of the velocity, and we're gonna derive it for the acceleration. So the velocity of point A, is the first time derivative of RA. And the first time derivative of RA is equal to the first time derivative of RB, origin of point B, and plus omega crossed by the relative position in the frame, and plus the relative velocity with okay, plus the relative velocity. Okay, like this first. The second time derivative of point A. What should be the second time derivative of point A? Again, for point B, the point B just translate on the global frame. Just translate on the global frame with the direction I and J, and never change the direction. So if we want to explain the acceleration of point B, it's straightforward. You can just obtain the second time derivative of the position vector of point B. But for this term, to take the time derivative of this term, you may need to think about d omega by dt, and then cross by the relative position, and plus by keep omega as a constant, and cross by dr by dt. You see this term, when you want to obtain the time derivative of this term, you need to dip omega by maintain r, and you need to maintain the omega and cross by the time derivative of the relative position r. And for the dip of the last term, the relative velocity is x dot in I direction plus y dot in j direction. The relative position is x I plus yj in the moving and rotating frame. the relative velocity is the velocity with respect to that moving frame is x dot I plus y dot j. Be careful that the time derivative of the relative position is not equal to the relative velocity, because the relative, if you come back to the order of the velocity, you can see that the time derivative of the relative position consists of two parts. The first one is the relative velocity, and the second one is consider the omega crossed by the relative position. When we consider the relative position is a constant and doesn't change magnitude against time, just change the orientation. So be careful. The first time derivative of the relative position is not equal to the relative velocity. The first time derivative of the relative position equal to the omega crossed by the relative position when we consider the change in direction change by maintain the magnitude. And when we consider the change of the magnitude, it will be the relative velocity magnitude of a relative position change. Be careful. Also, we also have the relative acceleration. By the concept, the relative acceleration is also the change in the magnitude of the velocity with respect to the direction x, the direction I and j direction. And okay, come back to here. For the relative velocity, the velocity of point A is equal to the velocity of point B plus the relative velocity and the omega cross r. This is the first time derivative. If we consider the second time derivative, the second time derivative of point A, position vector of point A, is just change from r dot to r dot dot. And for point B, point B just translate on the frame, global frame. So acceleration of point B is nothing complicated. It's just r dot dot. And the time derivative of omega cross r, we have the first term and the second term. And the time derivative of the relative velocity is this term. So what next? Acceleration of point A. Acceleration of point A can be described by acceleration of point B. And d omega by dt, we know that omega is equal to magnitude multiplied by the unit vector. Okay, hey, I'm sorry. I lost my connection. But we're still in the class and the class still record, right? I hope the class still record. So let me share the screen. Okay. Okay, d omega by dt, omega, the angular velocity, is the magnitude omega with the direction k, d omega by dt is d omega by dt in the direction k, and omega multiplied by dk by dt. But the unit vector k is constant because it's never changed the direction. In our case, on the rotation about the axis perpendicular to the plane, the direction of the k always point out from the screen, perpendicular to the screen, and never change the direction. So d omega by dt is not complicated. is just alpha crossed by the vector relative position vector r. What about dr by dt? dr by dt. This one. Dr by dt. Dr by dt. Dr by dt is equal to dr by dt is d by dt of xi plus yj. Xi plus yj. So we have x dot I plus xi dot plus y dot j plus yj dot. So when we consider the I dot and j dot, and when we consider just x dot I and y dot j from the previous page, if we still remember here, this one is the relative velocity in the direction x and I. And this one is omega crossed by xi plus yj. Omega crossed by xi plus yj. Omega crossed by xi plus yj is equal to x multiplied by omega cross I plus y multiplied by omega cos j. But we know that hey, omega cross unit vector I is the first time derivative I dot. Omega cross j is also j dot. So from the previous page, we already obtained the time derivative of the relative position. We already do it. And again, it's this one. So how about the relative velocity? The relative velocity. When we need to obtain the first time derivative of the relative velocity. Again, I'm sorry. Before that, why we need to check r dot? Why we need to check dr by dt? Because omega cross r, when we obtain the time derivative, it will be d omega by dt cross r, and omega cross dr by dt. d omega by dt is just alpha cross r. It's simple, but the second term, it should be omega crossed by dr by dt, and dr by dt, we have two terms. We have omega cross r, and we have the relative velocity. We have two terms. The last term, this one, The last term is this one. How can we obtain this? This one is the first time derivative of relative velocity. Relative velocity is considered in the direction I and j, and consider the change in the magnitude against time of x dot and y dot. d by dt of the relative velocity, d by dt of the relative velocity, we consider x dot as a constant and consider I dot, y dot as a constant and consider j dot. And for this one, we consider I and j constant and x dot have one more time derivative. Y dot have one more time derivative. The first term, this one, the first term, this one, I'm gonna do the similar way. I'm gonna do the similar way as this one. Omega crossed by a vector. What should be omega crossed by the relative velocity? Relative velocity is x dot in I direction plus y dot in j direction. Omega crossed by relative velocity may equal to x dot, and just consider omega cross I plus y dot and omega cross j. And what should be omega crossed by unit vector I? Omega crossed by unit vector I is unit vector I dot. Omega crossed by the unit vector j is j dot. So the first term here, can be described by the physical meaning is the omega crossed by the relative velocity. And the last term here, is the relative acceleration. Just consider the second time derivative of position x and position y in the direction I and direction j, and not consider the effect of the direction change. So the final term, the dip of the relative velocity, we have omega cross relative velocity plus relative acceleration. So to summary, to summary for the relative acceleration. The acceleration of any point on a moving rigid body can be explained by the acceleration of the origin of the frame, the moving frame, and consider the effect of the angular acceleration, and consider the centrifugal acceleration, And you can see that we have omega cross V relative here, omega cross V relative, and we still have another one, omega cross V relative. So the total will be 2 multiplied by omega cross V relative, and this term is Coriolis. We will have a short example to explain the meaning of Coriolis in the next slide. The last term here is the relative acceleration. The relative acceleration consider the x dot dot with respect to I and y dot dot with respect to the j direction, and not consider the change of direction in this term. Okay, Coriolis. I'm not expecting that we have the complete or the complete explanation or the clear of the Coriolis. I mean, it's a complicated thing, but at least I expect that this slide will give you an idea or support you for future study if you want to read more about Coriolis. Actually, they have the extensive explanation in the textbook, but I try to pick some point to describe in our class. From this slide, we mentioned that we have point P and point A. And of course, P is fixed to the frame. P doesn't have the relative velocity, relative acceleration respect to the xy. But point A can move along the path or can have the relative velocity, relative acceleration, or change the relative position of point A with respect to the frame. So A and P can have the relative acceleration between them because point P is fixed with the frame, but point A can move along the plane. And with our analysis, we have the rotating axis in this week class, and in the previous class we mentioned about the translating axis. So point A and point P point A and point P, point A and point P, of course, they have the acceleration of A relative to P. And with the analysis, when we use the rotating axis method, we can see the terms of the acceleration. And the definition, one explanation of the Coriolis, not the definition, but just one explanation. One explanation is, hey, we have the relative acceleration between point A and P. P is fixed to the moving frame. Point A can have the relative velocity with the moving frame. And by using the rotating axis, when we consider the rotating axis, we can see the effect of the acceleration differ from using the non-rotating axis. Yeah, just one explanation. Maybe we cannot get the clear picture about the Coriolis, why we need to have omega cross V one time and need to plus it again with the omega cross V. So let's see this simple case, why we call this is a simple case because the point A, in this case, the point A just move along the x-axis of the moving frame. Point A cannot move in the y-axis. It can move only in the x-axis. In this case, we have the global reference x and y. We have the global reference x and y. And there is one rotating point at point O, or at the origin of x and y. So it's simple. Why is simple? Because now, if we consider the position of point B, the velocity and the position of point B, maybe for the position vector, we may need to write RA equal to RB plus something, VA equal to VB plus something, and acceleration. But in this case, point B, or the origin of the moving frame, is placed on the origin of the global frame and is fixed. It's never change the position. It's never change the velocity and never change the acceleration. It always be zero in this case. And the relative velocity is just only in the I direction. And it constant also. Relative velocity is constant, which means if we consider the relative acceleration, relative velocity is x dot, is constant, and of course x dot dot is equal to 0. Of course, in this case, y is 0, y dot 0, y dot dot also 0 in this case. But just only one thing that can change is the relative position x. So velocity okay, if you see the velocity in this case, we can, when we explain the velocity in the frame, we can have two components of the velocity. We know that we have the relative velocity just only in the I direction, and this is not okay. We need to it should be better to explain by this with the global velocity of point A equal to velocity of point B plus omega cross R omega cross R and plus the relative velocity okay. Velocity of point A in this case we select point B at the origin of the moving frame. So the moving frame, as I mentioned, is fixed position. So point B or point O point B or point O have 0 velocity. Omega of the rotation is omega k r or the relative position of point A measured from the origin of the moving frame is xi. Position r is xi, and relative velocity is x dot in the direction I only. So what is omega k cross xi? What is omega k cross I? K cross I will be j, right? So is omega x j and plus x dot I. This is the velocity of point A with respect to the global frame. Is that make sense? Is that make sense? From here? Of course, if the x dot, the point A is moving with the moving frame and have the relative velocity, although we are not consider the effect of the relative velocity, point A is moving with the moving frame. And if point A has the position far from the origin of the frame, and the frame rotates with omega, and the frame rotates with omega, the velocity of point A is point to the direction of J, is point to the direction of J. And the magnitude of the velocity as the effect of the rotation is equal to omega multiplied by the radius or the distance from the origin. And if we consider the relative velocity along the slot, we can have the relative velocity in the I direction. So this is the velocity vector of point A with respect to global frame, but we express it in the terms of the unit vector I and j. But please keep in mind that the direction of I and j is not the same with I and j of the global. I and j is the unit vector of x and y that can change the orientation. It's the rotating axis. And this is the velocity. So what is the d by dt of velocity of point A? What is the d by dt? We have omega xj and x dot I, right? We have x omega j and x dot I. I will try to do from the first term x dot I first. So d by dt of x dot I will be x dot dot in the direction I plus x dot as a constant and I dot. And for x omega, the dip of x omega j can be x dot omega plus x omega dot when we consider the constant, the non-change direction j. And when we consider the change of the direction, we're gonna have j dot. And we have x dot dot I plus, do you have any idea for I dot? The unit vector I dot will be omega k. I dot is equal to omega crossed by unit vector I, but omega is the magnitude with the direction k and crossed by I. So k I will be j. So I dot is equal to omega j. I dot is omega j. So x dot multiplied by I dot will be x dot omega in j direction, and x dot omega in j direction plus x omega dot in j direction. And what should be j dot? What should be j dot? J dot is equal to omega crossed by j. If you want to obtain the time derivative of a vector with a constant magnitude, if you want to obtain a time derivative of a vector with a constant magnitude, you just cross that vector by omega vector. Unit vector j can change its direction, but it never change the magnitude. Magnitude of the unit vector always be 1. So j dot is omega crossed by j. Omega is magnitude with the direction k, and we cross it by j. K cross j will be minus I. K cross j will be minus I. So j dot is minus omega I. J dot is minus omega I. So we have multiple terms here, but this example is simple. It's simple because omega is constant and x dot is constant. X dot is constant means x dot dot will be 0, and omega dot also 0. So finally, in this case, what can we obtain is acceleration of point A. Acceleration of point A is equal to these two terms minus omega square x minus omega square x in the I direction, and 2 omega x dot in j direction. Of course, we're familiar with this. It makes sense if you look it by eye, when the point A rotating about this, rotating about the fixed center of rotation, we have the centrifugal acceleration with the magnitude of omega square multiplied by the radius, and the direction of the centrifugal acceleration is point toward the center of the rotation. It means it points from here to the negative I direction. What is this term? What is the meaning of the Coriolis? Coriolis will exist. Coriolis will exist in the J direction just only when we have x dot. If x dot is 0, if the relative velocity is 0, Coriolis will be 0. But if x dot is non-zero and we have the relative velocity, we can see the effect of the Coriolis, and the Coriolis from the derivation, we can see that it comes from two components. Why not we check this picture to see the physical meaning of these two components, how it comes from. We begin from the velocity vector. And the velocity vector consists of two components. The first component is the relative velocity along the x-axis. The second component of the velocity vector is due to the rotating of the frame with the radius x and the angular velocity omega. The direction of x omega will point in the direction of the y-axis. X omega will point in the y-axis. X dot will point in the x-axis. These are two components of the velocity vector, and of the change in direction, the effect of the change in direction of the velocity vector. The change in direction means when the time pass, the axis shift from x to x prime and y to y prime. The axis shift from x to x prime and y to y prime. The small distance here, or the magnitude of the vector, is equal to x dot d theta. X dot d theta as the effect of the relative velocity. If we have the relative velocity, and the axis are rotating, the axes are rotating, you need to imagine that we have the relative velocity and the axis is rotating. So we have the acceleration, which is the change of the direction of the velocity, the change of the magnitude of the velocity. Before the axis rotates, we have x dot in the x direction. After it rotates with d theta, the new relative velocity will point in the different direction. And the difference of the velocity against time, a short time, we will have this magnitude of the velocity difference. So if we do this by dt d by dt of the x dot d theta, we're gonna have the omega x dot. We're gonna have omega x dot in the j direction. And how about this x omega component? We talk about the x dot component, the acceleration, that is the effect of the x dot, or the acceleration, that is the effect of the relative velocity, will appear in the x dot omega in j direction. Please don't ask me why we cannot see the x dot dot. In this analysis, we consider the constant magnitude and consider the change in direction. Consider the change in direction. And we have x dot omega as the effect of the acceleration here for the effect of the relative velocity. How about the effect? How about the effect of x omega? How about the effect of x omega? X omega consists of two parts. We have x omega with the direction change d theta. So x omega d theta by dt will have the direction of minus I, which gonna be omega square x in the minus I direction, or the centrifugal acceleration. But for the Coriolis, x multiplied by omega. X multiplied by omega means the x distance from the origin and multiply by the angular velocity omega. We have the magnitude of the velocity x omega. But we should consider the effect when the relative velocity is not zero. The relative velocity is not zero. It means that, hey, if the point A slightly shift the position, if the point A slightly shift the position, and we have the dx, it's gonna affect the magnitude of this vector. the magnitude of this vector, can be changed by two possible ways. The magnitude of this vector can be changed by two possible ways. The first way, when the omega is constant, but we have the dx as the effect of the relative velocity. The second way, although x doesn't change the position, but we change the speed of rotation. If we change the omega, it also affects the magnitude of this vector. But in this simple case, omega is constant. So d omega is 0. We just consider the effect. Of the change of the dx, or the effect of the relative velocity over the time. So yes, here we also d by dt of x omega will equal to omega dx by dt, or the omega x dot, and the direction will be the j direction. So now, until now, in this picture, we can see three sources of acceleration. The first one is this one, the origin one. This acceleration is the effect of the change in direction of the relative velocity. The change in direction of relative velocity. We have x dot multiplied by omega in the j direction. The second one is the change in direction of x omega, the change in direction of x omega, and it will be in the minus I direction, which is the centrifugal acceleration. The last term comes from the effect when we change the position over time, which is the relative velocity. If this multiplied by the omega, of course, we're gonna have the acceleration in the positive y direction. But yeah, the x dot omega from both two sources, they have the same positive j direction, and we combine them, and we name it as Coriolis acceleration. Yes, a long derivation, and let's have a break before we start this simple example and continue with our previous week's problem. Let's have 10-minute break. And please come back by maybe 3, 5, 10-minute break.